Hello, AP Stat students. Mr. Hazelhorst coming to you live today from room A08. Today we want to talk about some modifications that you can make to experiments to try and improve their design. This is kind of similar to when we talked about sampling and we said, okay, a simple random sample is the best way to go about selecting a sample, but sometimes it's not always the best way. We might use a modification. We might use a stratified random sample. We might use a cluster sample. And we can make some improvements to that design of random sampling. And we can do the same thing with experiments, all right? So some quick thoughts about experiments. A completely randomized design for experiments where we just take our people, we randomly assign them into a treatment and a control group, and then we compare them in the end. That's our simplest proper design for an experiment. But our simplest method doesn't always yield the most precise results. And so we want to go through two types of modifications that we can make today, kind of explain why we would utilize those. And then just to give you a heads up, next week in class, we're actually going to do some activities in class where we actually perform these modifications, and you can see how they have a positive impact on the results of a study. Not a biased impact, not a negative impact, but they help clarify what we're actually seeking through an experiment. Now, they don't always work. They're not always the best thing to use, but in certain cases, it makes sense to use these two types of modifications. So let's jump into our very first one. The first type is what's known as a randomized block design. And this is where the random assignment of our experimental units or subjects in terms of deciding what treatment they get is carried out separately within each block. Now, that definition doesn't do us any good unless we understand what a block is. And so a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatment. All right, the most common block that's utilized is gender. We recognize there are biological differences between males and females. And so a lot of times in medical studies, they recognize the impact that gender can have. It can be a major lurking variable if we don't try to control that. And so gender is a situation where we would use a block. So essentially what we do is we take our group of experimental units or subjects and we say, okay, we know that gender is going to have a huge impact on the results of the study. So the very first thing that we're going to do is we're going to split gender up. All right, we're going to put all the males over here. We're going to put all the females over here. And essentially, we're going to run two similar experiments within each of those blocks. And then we can still carry out all of our fundamental principles in terms of randomization, comparison, replication, and control. But we eliminate that confounding or lurking variable of gender. Okay? And this is a great modification that is used very, very often, okay? Because again, sometimes we recognize the impact that other variables might have on a study. So let's take a look at an example, and we'll go through the process of diagramming out a block design experiment, just like we did the other day with our basic comparative experiment. All right? So here's our example. All right, a high school regularly offers a review course to prepare juniors for the SAT. The school wants to compare the effectiveness of an online prep course to a typical class prep course to improving math scores. It is known that the current math class, we either have students in pre-calculus or algebra 2, impacts a student's math score simply because of what they've covered in that class. Typically students who are a little bit more advanced are probably going to score better on an SAT, especially in the math section. And so, the class that they're in is a major confounding or lurking variable, right? So we know that the school has 50 students taking pre-calc and 60 taking algebra 2. And so we want to set up an experiment that takes into consideration the impact that the current math class could have on a student's score. All right. So when we diagram out this experiment, it's going to contain a lot of the same characteristics that we saw with our completely randomized design. So we begin with how many students we have to utilize. And when we take a look here, we have 50 pre-calc and we have 60 algebra 2. So we have 110 students at our disposal. Now, you might remember in our completely randomized design, our next step was to randomly assign. Well, that doesn't happen in a block design first. All right, what happens first is the block. All right, recognizing, okay, current math class, you could have a huge impact on the results of the study. So we want to block you. All right, so the very first thing that we're going to do is we're going to take and divide them up by this possible lurking variable. So we're going to say, okay, all pre-calc kids, you're up here. And we know that we have 50 of you. And all Algebra 2 kids, you're down here. And we have 60 of you. And it really doesn't matter that our groups are not equal. That won't have a huge impact on the results of the study. Because again, essentially what we're going to do is create two experiments within one big experiment. All right, so pre-calc kids are going to get compared to pre-calc kids, and Algebra 2 kids are going to get compared to Algebra 2 kids. All right, so now that we've set up a block, now we go ahead and apply our random assignment. And we need to do that in each group. All right, and so the pre-calc kids, we're going to take and we're going to randomly assign them into two different groups. Right? One of them is going to have an online prep class, and the other one's going to have a typical class prep class. All right? To show replication, we're going to show that we are evenly dividing these two groups up. So the online prep course gets 25, the in-class prep course gets 25 students. And we're going to do the same thing down here with Algebra 2. Right? We're going to have a group that goes to online prep. We'll have 30 of those. And we're going to get a group that goes to our in-class prep. Again, that's going to be a group of 30. All right? And then our next principle to show is our comparison, right? So what do we want to compare? Well, we want to compare their SAT math score. And we're going to do the same thing down here. All right, we're going to compare. Again, we're going to compare the SAT math score. And then at the end, we want to take and we actually want to combine these results together. And what a block design allows us to do is to actually gather some more information. Again, recognizing how these different math classes could impact their SAT math score. Now we might get done with this experiment and say, you know what? We really don't see a significant difference in the online prep course with the pre-calc kids. So we don't need to spend the money for them, but we did see a statistically significant difference in the Algebra 2 kids. All right? And because of the block and because of us eliminating that lurking variable, that would become more clear. All right? Now, again, we might see that it works for both, and we might see it works for neither. But again, it just gives us more information. And in situations where we know we have a major lurking variable, a block design is the ideal design to an experiment that we would want to set up. Okay? Now, I want to point out that we still have all of our key components. Right? So we think about control. Well, we still have our control set up with our treatment and our control group. We still have randomization. We still show replication by the even distribution within our groups. And we still have comparison. All right? All of those things are still present in the design of this experiment. So it's a modification that is a good one. Because again, we are still containing all of those key principles of experimental design. All right, now the second type of modification that we want to talk about today is what's known as matched pairs design. And there's actually two types of matched pairs design. All right, just the name itself kind of gives us some direction, right? We're going to match things together. And so one type of matched pairs is when we take each experimental unit, all right, and we give them both treatments, one after the other. All right, now, order could have an impact on things, so we're going to randomize that order, and we'll talk about that in an example here in a moment. All right, and comparison occurs by comparing experimental units to itself. And this, again, is a very common modification that is made in experiments because we recognize, especially with people, just how different people can be. So to put me in an experiment and to put you in an experiment and to compare the two of us, well, we are so different that there are so many lurking and confounding variables that could be present there, that how do you eliminate those? Well, the easiest way to eliminate those is to compare you to yourself, right? Because you to yourself, a lot of those lurking and confounding variables are controlled by the fact that we're comparing things on equal plane, okay? The second type of matched pairs is where each experimental unit is paired with another experimental unit. They're randomly given a treatment, and then the comparison occurs within pairs. Now, this is a little bit harder to pull off because to match experimental units together can be extremely difficult. It's oftentimes not utilized with human subjects. If it is utilized with human subjects, this is where twins are extremely valuable to the research community, because twins are almost the best pair that you can make. Oftentimes, their gene pool is extremely similar, right? Their home life has been extremely similar, so a lot of those confounding and lurking variables can be controlled utilizing twins. They're not perfect, but it does make a huge difference. If we're going to use this type of matched pairs design, though, it's often utilized with non-human experimental units and non-animal experimental units. Maybe we're talking about testing the strength of a new type of desk or something. With desks, it's a little bit easier to pair them together and know that a lot of those lurking variables are controlled. All right, but let's go through an example of our first type of matched pairs and see what that would look like in a diagram, okay? Now, why matched pairs? Again, the whole idea is we want to minimize the impact of confounding and lurking variables. So let's take a look at this example. Let's say we wanted to design an experiment to test, does talking on a hands-free cell phone device still distract drivers? We know that we're not supposed to hold our cell phone, and so a lot of vehicles now come equipped with some sort of Bluetooth hands-free device. But the question is it really any safer talking on a hands-free device? Yeah, your hands are free, but your mental focus still isn't there. And so 40 undergraduate students have been chosen to drive a simulator that's equipped with a hands-free cell phone device. And in the simulator, they're following a car. And the car ahead of them brakes suddenly. And so the question is, how quickly does the subject respond? Right? So, obviously in this experiment, it would make sense. Well, we need some people to drive with a hands-free device and some people to drive without. But if we think about that, there are some major confounding and lurking variables that would be present, in this experiment if we just did a simple, completely randomized design. We recognize there are huge differences in the driving ability of people. There's huge differences in just the mental focus of people while they're driving. And all of those are things that could have a huge impact and introduce some bias to the results of this study. So we need to think about, okay, well, how do we manage that, right? I mean, would it do any good for us to compare response times if I'm a driver to you as a driver, right? We're different. Okay, the other thing too is just natural reaction time. Some people react quicker than others do. And that could have an impact on the results of our study, all right? So, what makes the most sense in this example is for us to say, you know what, I'm just going to compare you to yourself. I'm going to have you drive both ways. I'm going to have you drive once without the cell phone hands-free device and once with it, using it. And we're going to see, how does your response time change? And that controls all those lurking variables of just natural driving ability and response time and all those sorts of things. Now, we still need to show random assignment. And again, what we're going to randomly assign is the order in which a subject receives those treatments. And the reason for this is if I don't randomize the order could be a lurking variable then. Right? If the first time I have you go through and you're not using the device, all right, and then the car breaks, well, now you've kind of experienced this experiment a little bit, so you kind of have an idea of what to expect. And so, the next time, even though you're using the device, just because you've been through this experiment one time, you're a little different prepared. You're not treated the same anymore. All right, and so that could have an impact on the results. And that's, again, why we need to randomize the order. All right, so let's diagram out this example of a matched pairs design. All right, so again, we're going to start out with our number of subjects. Here we have 40 undergraduate students, right? And right off the bat, we're going to go into random assignment. All right, so we're going to evenly split this up into two groups of 20. Now, what we're going to randomly assign, again, is the order of the treatments. All right, so we're going to have one group that drives the simulator using the device. And then they're going to not use it. All right, so we're going to put 20 people in this group. And then the other group is going to go the opposite order of that. All right, they're going to go through the simulator the first time not using it. And then they'll go through the second time using the device. All right, again, we'll have 20 people in this group. Now, what we want to compare in the end, because each person is receiving both treatments, is we want to see the difference in those response times. All right, so as we compare in a matched pairs design, what we're comparing is the difference in response times. All right, and because we're utilizing a matched pairs design, a lot of things are possible here. If we see a huge comparison or a huge difference in response times between when they're using it and not using it in both setups, well, then we know, yeah, okay, you know what? Hands-free devices are still distracting. But let's say in this example, they're using the device and then not using it, and we don't really see a huge difference, and or whatever. Again, it's going to just help give us more information. We might see that, really it's just a placebo effect. All right. There's some other lurking variable out there controlling or having an impact on the results of this study. All right. Now, point out again, we have all four characteristics of proper experimental design in place. We have randomization, right? We have control as we're going in the different order, right? So we have one group, we're again minimizing that lurking variable. We have replication, and we have comparison. Okay? And so even though it's a modification, it's not changing or taking away those key principles that we know need to be in place. All right. Well, I hope that gives you some understanding of our two different modifications that we can make on experiments. And again, we're going to go through some examples next week in class that I hope will help illustrate the importance of these two types of modifications. They don't always work, and we'll see that next week. But in the right situations, they can make a huge positive impact on the results of our study and really clarify things for us. So your homework assignment today is on page 262, in your ebook, page 290, problems 75 through 85 odd. So I hope you guys have a great day, and I will see you soon.